Okay, hi everyone. Good morning. Welcome to the today's class. Okay, so we would like to discuss about lecture number. It is two. It's two. Yeah, three. Lecture number 3. Unit number 3. Okay. So we have been discussing about mass transistors. Okay, so let us continue this one. So let us recapitulate what we have seen in the previous class. Okay. What we have identified in the last class. So we have seen the important part of the mass transistor. Okay. That is called mass capacitor that we have seen, and the related structure we have seen, and what are the different modes that are available in mass capacitor by applying the different potential between the upper plate and bottom plate. Okay, so let us quickly recapitulate what is that. The first one is called depletion accumulation. This is the one mode that the mass capacitor has got this kind of mechanism. And next one is called depletion mode. And the third one is inversion region. Third one is inversion region or inversion mode. Okay, so this is what is very important to note that for a mass transistor, we would like to operate on. We have to bring the mass capacitor for the inversion mode of operation. That means we have to apply a positive potential at the gate, at the top plate. For example, what I'm trying to say here is we have a mass capacitor, something like this. Okay, we have a capacitor here. Bottom of that one, we have a bulk, right? So therefore, this is what we know very well about that: metal, oxide, and semiconductor. So by applying some potential difference between these two plates, upper plate, metal is upper plate, bottom plate is a semiconductor. By applying different potentials between these two, and we can see this kind of mode of operations of the mass capacitor. If you want to understand the MOSFET operation thoroughly, so inversion mode of operation is very important for us. Okay, so that's what we have understood from the previous class. The second one is mass structure, right? Mass capacitor structure. Okay, that means we have modified this structure, mass capacitor structure, in order to form a transistor. Agreed? Okay, let me do this. And copy and paste. I think today my system is somewhat a little bit slow. I hope. Please cooperate with me. Okay, this is the mass capacitor, right? Okay. So what we have done, we have included some extra material. Okay, that extra material we have included here. Sorry for that. Extra metal here and some extra metal here. Okay, so this is all about sourcing and getting the carrier transportation between these two. Okay, so I have used the extra terminals here. This is the one terminal. Okay, this is another terminal. These are the two terminals I have considered. So altogether, what we can observe that we have 4 terminal device we have constructed. Okay, so we have already given name for the source. We have given this is the gate, and this is given name as drain, and this is called substrate or bulk. B for bulk. Okay, so agreed. Bulk. So this structure that we have created previously. Okay, if that is the case, and I don't want to show you this lines, something like this, not necessary to do this, because everything is the same. Okay, Essentially, this is what we have constructed previously. Okay, in fact, actually bulk is very thicker semiconductor that we have to consider, but for the sake of simplicity, I have written very small area, small thickness only I have considered, but it's a very big one actually. Okay. Okay, so now, and the third part also we have seen what are the, how do we apply the potentials for this one? So the mass capacitor, it's not a mass capacitor structure. This is the above one is a mass capacitor structure. It is mass transistor structure. Okay, mass transistor. Okay, mass transistor structure. Agreed? Okay. Now, the third point that we discussed about it is how to apply the potential difference between these terminals. Okay, we are very much clear about it. Okay, so one connection is we have to apply the potential difference between gate and drain. Okay, sorry, gate and body, right? Agreed. So I think better we have to apply some potential difference between these two. Why we need to apply the potential difference between these two? Anyone from the class? Why we need to apply the potential difference between gate and bulk? Can you type it in the chat box? Can you help me? What is the reason why we need to apply the potential difference between these two? Anyone from the class? At least one response or some few responses I need to have. Yeah, thank you. To bring the minority charge carriers to the surface. That's absolutely right. Another one response is to create a channel between the source and drain. Exactly. Thank you very much. Thank you, both of you. Okay, that's the reason why we have to apply. Since it is a positive, okay, since this substrate is a p-type substrate, p-type substrate or p-type bulk, okay, substrate and bulk one and the same. Please remember that. I'm using the word called substrate, which is equal to say that bulk. Okay, so we can interchangeably call sometimes a bulk, sometimes I want to call it as a substrate. Okay, that means a base material, nothing else in it. A semiconductor, simply a semiconductor. Okay, if it is a p-type of substrate, it's very important to note that if you want to have a minority carriers, we should apply a plus positive charge on top of the metal, and we have to apply negative charge at the bottom. Agreed? That's what we have seen in the last class. Okay. Yeah. Once we have a minority carriers under the silicon dioxide, under the oxide, we have applied the, we would like to transfer the carriers that is available from source place to the drain place. Okay, so plenty of electrons, minority carriers are available here under the silicon dioxide, right? Because of the gate and bulk. Now we would like to transfer the carriers from source side to the drain side. Then we have to apply the potential difference that is called, we have to apply some potential difference between the gate and source and drain. By the way, what is the charge at the source side and what is the supply terminal for the drain? Okay, so yeah, the source side must be what type of source, what type of charge that we have to apply? Can anyone? My question is, in order to push the electron from the source side to the drain side, what is the polarity of the battery that we have to apply at the source side? And what is the polarity of the battery that we have to apply at the drain side? As we have mentioned that gate to body, we have a plus and minus at the body. Okay, so that's what we have given in the last class also. Okay, so it must be a negative. Yeah, thank you for your response. Negative at the source and positive at the drain. Exactly. Thank you very much. So negative at this one and a positive at this place. Okay. I think it's a little bit bigger, I think so. Huh? Yeah. That is the polarities that we have applied. Okay. This is all about the things that we have seen in the last class. And the symbolic representation also we have seen. This type of transistor is called N channel. This is called N channel MOSFET, right? That is what we have given the name. And we have also mentioned that the symbolic representation of this MOS transistor, right? Okay, I'm sorry. It is something like this we have shown yesterday. Okay. So, and this is called bulk, this is called gate, this is called drain, this is called source, this is called body. Okay. So therefore, when we talk about, when we are designing some circuits, the structure is not advisable to draw all the time. So instead, we would like to use symbolic representations about it. Okay. Now, fine. And I mentioned that it is actually an enhancement mode type of transistor. Okay. Enhancement. And we have defined that the transistor can be a enhancement or depletion depending upon whether initially inherently the channel is available or not. If inherently channel is available, it is called as a depletion mode type of transistor. Or by applying the potential difference between the gate and body, if the channel is formed, then it is called enhancement type transistor. Okay. And one more thing is that another point I would like to say that N-channel MOSFET only we have seen. What does it mean? The channel between the layer between the source and drain is a N-type channel. Okay, N-type carriers that are available. So there is a possibility of the P-type carriers. Can you guess if it is a P-type channel, what kind of substrate should be, and what kind of source and drain should be? Any guess? Any guess? The question is that if you want to have a p-channel transistor, p-channel MOSFET, can you guess what is the, of course, consider the enhancement only. What is the source? Okay, what is the drain? What is the channel? What is the bulk? What is the bulk? Can you guess? Can you fill this table or fill the question? Very simple to understand. Okay, it will be very easy. Source should be a, because the bulk should be, what is the bulk should be? The P channel, P carriers are required. Okay, I would say that P channel is required, right? P channel means, can we get the same P substrate? Can we get the same P substrate? No. Why? Because if you use the P substrate, holes are the majority carriers. Okay, but we would like to have holes should be a negative. So holes should be a minority carrier. Okay, which substrate or which type of semiconductor will have minority carriers, P minority carriers, or holes are the minority carriers? You know that it is a N-channel MOSFET, N-type substrate, right? N-type. Agreed? If it is an N-type, then the holes are minority carriers. Okay, so that's what we have to change the P substrate to N-type substrate. Okay, and then we have to facilitate that the source of carriers, this type of source, N-type carriers, we have to provide. Sorry, P-type carriers that we have to provide. Then we have to have P plus, and this is also must be a P plus. This is how we have to define that. Agreed? Okay, that's what I would like to say about it. And yeah, so another point also we have discussed it previously, but actually this is not discussed in the last class, but we have not done anything about it. But please remember that there is a chance to understand about it. Okay, in the last class we have seen again some point that whenever we have a MOS transistor here, something like this, and how do we differentiate between the source and drain? Because the source and drain are at the same type of materials. Okay, N plus materials only. How do we say that one is a source, one is a drain? If I say that, for example, this is the source, this is the drain. Okay, if that is the case, what we have to understand. So, for example, if you give a negative, if you give a positive terminal to this, okay, that means if the drain, if top plate, so for example, this one, if the top plate is more positive than the bottom terminal, then it is called, then we have to name it as drain. Okay, and we have assigned this negative, that means not negative actually, when compared to the upper terminal, if it is in smaller one, then it is called source. Okay, if you say that if it is upper one is uh, bottom one is more positive, for example, bottom terminal compared to the upper terminal, then we should give the name called drain for this one. Sorry, so drain for this, and this is the source. Okay, this is point, this point also we have discussed previously. Okay, fine. So far so good. Now let us consider about some qualitative analysis of MOS transistor. Let us consider the qualitative analysis of MOS transistor. So far so good. What, this is what we have seen in the previous class. Okay, all the things related to the MOS transistor. Right? Okay. Now let us talk about qualitative analysis MOSFET or N MOSFET. Okay, I can call it as N MOSFET. What does it mean? What do you mean by a qualitative analysis of MOSFET? Okay, let us consider let us consider a MOSFET is something like this. Okay, by the way, I would like to take this diagram once again. Yeah. Okay, fine. So look at here, actually, we need to give the voltage names between the terminals. Let us give some terminal names, whatever the potential difference that we are applying. So far, we have not given the names. Okay, just some voltage that we have applied here, as I mentioned that. Some voltage is applied here, suppose some V1, for example, and this is called V2 we have given. Okay, but specific names that we have not given, so let us consider about it once again. Okay, so V1, what do you mean by the V1 here now? V1 stands for the voltage difference between uh, voltage difference between source and drain, right? Sorry, I'm sorry, the voltage difference between drain and substrate, sorry, drain and source. Don't confuse, this is the drain, this is the source. So that is what the potential difference we are applying. So it is called Vd minus of Vs, right? Vd minus of Vs. Of course, we need to write positive terminal first, then negative terminal, we need to write it there. Okay, or I can say that the potential, this is what the potential difference, right? Fine. This is also say that VDS also. This is also, we can say that VDS. Okay, this is a name that we have to use all the time in our coming lectures also. So the moment if I'm writing the VDS means the potential difference that we are applying from drain to source. Okay, right? Fine. So similarly, what about V2 here now? V2 is actually the potential difference between gate and bulk, right? Gate and bulk. So this is called VGB. Normally we can call it VGB. Normally we can call it as. Okay, but actually there is a problem in this generation of V2. Actually, there is a problem with the V2. Okay, so there is a problem with V2. What is this V2? Generally, if you observe in this diagram, the source is at a negative potential, body is also at the negative potential, right? Source is at negative potential and body is also at the negative potential. Instead of taking the two negative terminals, something like this, okay, we can keep it as the negative terminals are kind of negative, the negative terminal of the supply is connected to at the same place, okay, which means that I don't want to use these connections, something like this, okay. I don't want to use something like this. Instead, I'm writing in this way. So I'm going to connect this source and bulk at the same potential. Source and drain at the same potential, because the negative terminal only we have to apply for this NMOS transistor, for the body as well as the source, right? And I'm going to apply the potential difference between gate and drain. Sorry, gate and body. I'm extremely sorry. Gate and source. Okay. So now I can place it. This is a negative. This is a positive. Okay. This is a negative and this is the positive. If we do so, another advantage of removing the different terminals for the bulk and source, another advantage is that we can reduce the body effect, or we can eliminate the body effect. Okay, the term I'm using here is a body effect. Body effect. So body effect means, what is it? What do you mean by body effect? So why we need to use the bulk and source are at the same potential? Why it must be at the same potential? The reason is that we have to avoid the body effect. Okay, so that's what we have to remember here. So to avoid, what I can write in it, to avoid I can say that, okay, to avoid body effect, we need to connect the source and effect. We need to connect our source and bulk. Okay. Now, what do you mean by the body effect? Actually, so the body effect means if suppose the source and body are at different potentials. Okay, of course, it is a negative only when compared to the bulk. Okay, so sorry, when compared to the source and bulk. So let us compare with these two things, bulk and, see here we can write it source and bulk. Both are at negative potential only. Okay, negative terminal only we have to connect it there, right? But of course, there may be a possibility of different negative values. For example, it is for example -3. This is for -5. There is a difference between these two things, right? Agreed? Okay, so in that situation, what will happen if the bulk and source are not at the same potential? The depletion region that is formed under this place will be very, very high. So normally there is a depletion region is formed here. Okay, initially there will be a depletion region. Okay, so this depletion region will be increases. Okay, if the source and body are not at the same potential. What will happen if the depletion region is increases under the silicon dioxide? We have to apply more potential at the gate in order to attract the minority carriers. That means we are increasing the threshold voltage of a transistor. That means we need to increase the threshold voltage of a transistor. But actually, it is not advisable to play with the threshold voltage of a transistor because of the different potentials. Okay, because we need to apply more power to bring the the minority carriers under the silicon dioxide. Therefore, in that situation, if you don't want to modify the threshold voltage of any transistor, keep in your mind that body and source must be at the same potential. Okay, is it clear to all of you what is the body effect? Body effect means the threshold voltage can be varied by the different potential difference between the source and body. Okay, so this must be avoided. Okay, so in order to do so, source and body are the same potential in this manner. Okay, agreed? So now I can write it, this is actually VGS now. Okay, agreed? And instead of calling this V1, what I can call? It is called VDS. Okay. So the moment if I'm saying like this terminal is look like this. So let us consider this is the terminal. This is the symbolic representation. We have a bulk here, and bulk and source must be at the same potential. Now it looked like a three-terminal device only, right? It looked like a three-terminal device, but actually it is a four-terminal device. Intentionally, we want to connect the source and bulk at the same potential. So it's a drain, this is the source, this is the gate now. Now, what is the potential difference that we are applying here? What we normally call test. The potential difference between this one is called gate and source. What is the potential difference that we apply here now? It is called VDS. Okay. Now, where is the current will flow in this structure? How the current will flow in this given structure? Okay. So, because of the drain and source potential, the carriers are moving from source to drain, right? So, therefore, source to drain, the carriers are moving, right? These electrons are moving towards this side, right? Agreed? Agreed? Electrons are moving towards the drain side. What about the current flowing here now between the source and drain? As I mentioned that current will flow from drain to source. Okay. So therefore, what is the current will flow here now? Our interest is the current is flowing from drain to source. That is the reason why it is called IDS. That is called IDS. Okay. This is called IDS. Okay. So our interest is that we need to understand that. Okay. So we have to make sure that the transistor becomes on. Okay. Sorry. The transistor must be on. Okay. For that reason, I'm going to use VGS. Once the transistor is on, I want to evaluate the IDS value based on VDS. Okay. Based on VDS. Okay, clear to all of you? What's my point is that what I'm going to do here is that, so this analysis, what I'm going to do here is that I want to make sure that the transistor must be on. For that, I'm going to use VGS. And if you want to transfer the electrons from source to drain, that means I want to evaluate the IDS value based on VDS, right? Okay, that means, for example, if this is my transistor, okay, consider that body and bulk and the substrate are connected to the same potential. Okay, okay. Here I need to apply VDS value, and here I want to apply VDS value. Okay, here I want to apply VGS. I'm interested to write small letters only, but not uppercase letters. VDS value I want to write. Okay, so my interest is that what is the current flowing to this one that I want to see. Okay, so this is what we need to understand about the mass transistor analysis. Now let us see what will happen here actually. So our point of interest is that main important thing is that when applying the VDS value, how much current will be flowing. That's what we would like to do in the broad sense. Okay, I'm going to make use of VGS also. How VGS will be useful, we will see in this particular diagram. Okay, so that means that I want to see the IDS value. I want to see the IDS value, okay, by applying the VDS value. This is what my requirement is. So my point is here is that, is it clear to all of you what I'm trying to do here? Point is that by applying VDS value, how much IDS value I'll get it. So this is what the analysis that I want to do here. Without any mathematics, I want to do very simplest manner. Okay. So for example, if I say that VGS value is, we are not applying anything here. For example, 0. That means that we are not applying any VGS value. We didn't apply the potential difference between the gate to source. The moment if I'm saying that gate to source means it is a gate to bulk also. Okay. So what will happen in this particular diagram? Anyone from the class? Anyone from the class? What will happen if I'm not applying VGS value? What kind of characteristics between the VGS and IDS will observe? Anyone? The question I'm repeating, if I'm not applying VGS means I'm not applying the potential difference between the gate and bulk, for example. Okay, what will happen? Anyone? Yeah, thank you. IDS value is 0. Okay, fine. There will be no flow of current. Exactly. So that's good. So what is happening here is that when the moment if you are applying VGS is equal to 0, that means we are not applying anything. There is no availability of the minority carriers under the silicon dioxide, right? Agreed? So what means that whenever we have a source and substrate, something like this, source here and body here, we have a gate. On top of it, we have a metal. So if you're not applying any potential difference, where the minority carriers is observed under the silicon dioxide? Okay, this is the right thing. So where the minority carriers are available between the gate and bulk? No, there is no minority carriers at all. So if the minority carriers are there, how much potential difference that you apply here between these two terminals, the carriers cannot move, right? Because the channel is not there. Once the channel is there, then only we can move. For example, if you walk in a road, outside, when there is a road, then only we can walk. Otherwise, how can we walk? Where we have to go? Okay. Similarly, the same scenario is applicable here also. If the channel is not present, how much potential difference but that we apply between the drain and source, the carriers cannot transfer. Okay. So therefore, the IDS value is, as our friend told, that IDS value is equal to 0. Okay. So therefore, we say that the IDS value is equal to 0. So therefore, whatever the VDS value it is, whatever the change of the VDS value it is, the IDS value is equal to 0. That's good. Okay. So this particular point we can call it as, we have to give the name for this. This is called the MOSFET is in, NMOS is in off state. So this is what we normally call it as, right? Agreed? The MOSFET is said to be in off state, or technically we can call it as MOSFET is in cutoff region. Agreed? The MOSFET is said to be in cutoff region. Okay, so off state we can call it as, or maybe cutoff region also we can call it as. Doesn't matter. Okay. Now let us apply another case. Therefore, this is the one case that we have applied. Let us apply the second case. Now let us VGS values. So when will be the inversion layer will form? As I mentioned, that inversion layer will form if you apply a sufficient voltage between the gate and drain. Between the gate and substrate, right? That means a sufficient voltage is required. Okay. So therefore, sufficient voltage I am calling as threshold voltage, right? I can call it as threshold voltage. Okay. If this VGS value is equal to VTH or greater than VTH, for example, if VGS value is equal to VTH or maybe greater than VTH also, what we can observe? So here we observe that what we observe here is that no channel. I can write it here, no channel, right? Here is no channel. So by applying the VGS is greater than VTH, channel layer will be formed or not? Yes, inversion layer will be formed because the magnetic gas will attract it towards the silicon dioxide. Right? If that is the case, what we can say that without applying the VDS value, because of only the channel formed there, can we find the current flowing through that device? That's the question I can ask you. The point is that, see here, the question is very clear. So I have a gate oxide, we have a metal, so we have source and drain. So by applying the potential difference between these two, by applying the potential difference between the which is greater than that of the threshold voltage, but I didn't apply any kind of potential difference between the VDS value. Okay, but anyway, because of VGS, the channel is formed there. Fine, it's good. But I did not apply VDS value. Then is there any possibility of the current flow from source to drain? That's the question. Anyone from the class? Quickly. See, unless otherwise, if you're not exciting the carriers, they cannot move anywhere. Okay, so therefore, yeah, it can move within this channel, but because of the randomness in the random momentum of the carriers, the net current value is equal to 0. Because there is no direction, they can move anywhere in the channel. Okay, net current value is equal to 0. That is what the fundamental physics that we have learned, right? So without applying the VDS value, we cannot expect here also we can expect that. Okay, so if this is the case and we are not applying the VDS value is equal to 0, if that is the case, I'm talking about this is the case, IDS value is also equal to 0. Okay, if the no channel means IDS value, so I can say that here I can comment like this, IDS value is equal to 0. Here also IDS value is equal to 0. But a specific name is there for this one. So please remember that is called the NMOS is said to be in the situation, whatever the VGS value is greater than VTH and VDS is equal to 0, for example, or exclusively for VGS value is equal to greater than VGS minus of VTH, we normally call it as the MOSFET is said to be in on state. It's said to be in on state. But please remember that there is no current flow. Why we are saying that there is no current flow? Because of VDS value is equal to 0. Point is clear? Okay. Now the third case, let us consider. So therefore, the transportation of the carrier. Suppose it's meaning to say sense that we observe that yes, first of all, the transistor should be on. Therefore, we have to maintain that VGS is greater than or equal to VTH. There is no doubt at all. Now I'm going to vary VDS value. Okay, now I'm going to vary this VDS value according to this diagram. Okay, according to this diagram. Okay. Okay. Now it is meaningful to say that IDS value is not equal to 0 now. Am I right? Is not equal to 0. Am I right? Obviously, the carriers can move from source to drain. Current will flow from drain to source. There is no doubt at all. Okay, so therefore I want to say one simple point here is that, so if first of all you have to make sure that if the transistor is on or off, right? Make sure that the transistor is on or off. If you want to say that the transistor is on, or if you want to say that the transistor is off, for example, I want to say that the transistor is off. For example, I want to make the transistor is on. What is the condition has to meet? That is the first thing that we should notice. That means when VGS value is less than threshold voltage, can I say like this? Is it sense? I've got sense in this one. VGS value is less than VTH. Yeah, it is 0 means of course less than threshold voltage. If it is VGS value is greater than or equal to VTH, then the transistor is said to be on. That is what the first point you should notice. Clear? Now, depends on, so this is based on VGS, comma, VTH. That is the first thing that we have to notice, whether the MOSFET is on or off. If the MOSFET is off, obviously we can say that IDS value is equal to 0, no doubt at all. Okay, IDS value is equal to 0. This is the replication, therefore IDS this. But when VGS value is greater than VTH, we cannot directly say that. Of course, I can say that the current value is not equal to 0. It is not equal to 0. Right? So that what kind of behavior the MOSFET will show by applying different VDS values. Right? Are you getting what I'm saying? That if the MOSFET is on, off means we don't have any problem, because the MOSFET is on means the current doesn't flow there. But when the MOSFET is on means, then we have to focus on what kind of behavior it will show with respect to the VDS. Okay, that's what the thing that we normally concentrated on here at this point. Okay, copy, and then I want to paste it here. Okay, now fine. Now, what kind of behavior that it has to show? Can you assume that maybe whether it is going something like this, or maybe this one something like this, or maybe this is the way, or this is the way? Which way that it has to go? Whether which kind of relationship it has to go? That's an important one. Okay, because the VDS has a possibility of various values. Okay, let's investigate that one in just a couple of minutes. We will complete it as soon as possible without wasting much amount of the time here. We will move forward. Okay, generally IDS will follow two ways. Okay, here the IDS is follows in two ways. Okay, so there are the two ways it can go. One is called IDS value is in linear relationship with VDS. That is what I actually experimentally proven. Okay, so we need to understand how this one. I think you have done some kind of experimentation in EDC lab or EDC lab most probably. This is what you might have understand. Okay, when we keep on increasing the VDS value, IDS can be linearly with VDS. Okay, IDS is linearly relationship with the VDS value. This is what we might have observed. Okay, so another thing that we notice that IDS value is not in linear. IDS is non-linear. Not in linear means not non-linear with IDS, with VDS, right? So these are the two possibilities that normally considered about it. Okay, whether it is a linear relationship or it is a non-linear relationship. That's the only thing is that. Okay, so the question is that, think about it for the tomorrow's class. What voltage of VDS IDS follows linearly with VDS? What voltage of VDS is responsible for non-linear relationship with VDS? IDS is non-linear relationship with VDS. Okay, so I'll give you the hint here. Just you have to follow that. We know very well about it. VDS value, and this is called IDS value. So some part of time, as we have mentioned that this is actually following this one, and we name it as VGS value is equal to less than threshold voltage for this setup curve. And we notice that there is a linear relationship for this one, and it will go to non-linear relationship is something like this. Okay, this is what we have familiar with. This kind of relationship is observed that make sure that VGS value is greater than or equal to VTH, right? Greater than or equal to VTH. Okay. My point is that, so we need to say that what is the voltage at which, what is the voltage of VDS? Okay. So this relationship is holds good up to from this point to this point. This is the linear relationship. And from this point to afterwards, this is actually non-linear relationship, non-linear. Okay, this is called linear relationship. Okay, the point is that the understanding about what point of volt, what VDS value it is, so that it kind of behavior will show. So that is the point of discussion tomorrow, the next class. And please try to refer some textbooks and identify what exactly the meaning of this. What VDS value will make this kind of behavior. Some part of the VDS IDS will be linear. Some part of the VDS IDS is non-linear. I can say that a constant value. Okay. So this is the topic of discussion in the next class. And please try to refer some textbooks. Thank you very much. And if you have any doubt, please send it through the modules or maybe WhatsApp. I'm available to respond for all your questions. Thank you, one and all.